Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be discussing the concept of dominant and recessive genes. Now I appreciate that this kind of area of biology is something that's can be quite challenging for us to understand. So I really want you to make sure you take the time to treat this video slowly, take your notes carefully and methodically, and really pay close attention to what is being said. Watch back over it a number of times if you need to, try and get it all down. Okay, so just kind of starting off with a quick recap of some of the ideas that we've met so far. The first one is that inside almost all of the cells in your body, you have 23 pairs of chromosomes. Okay, so all the DNA instructions that your cells need to function and to make you who you are exists in these 23 pairs of kind of sets. One of each pair comes from each of your parents. Okay, so one from mum, one from dad. So your biological parents, obviously. And then we also encountered this idea that your genes, or kind of these sections of information on your chromosomes, give rise to the features that you have. So your hair color, your eye color, your height, your weight, within kind of reason, that those sorts of things all stem from the genes that you have. Okay, that you have two versions, because you've got two lots of every chromosome. That means you've got two lots of every gene. And each of those lots of genes, or the versions of genes, we call an allele, which is this word here, A-L-L-E-L-E. So two alleles for each gene, one from mum and one from dad. Okay, and so then what we also recognize is that you can have genes for particular features that you don't actually have. Or that the genes that you have may not give rise to the same set of features. As strange as it sounds, that's kind of what we were looking at in the last video, that this idea that not all genes are created equal. Okay, and we're now going to see if we can make sense of how that kind of comes together. All right, so let's say, all right, so we've got a particular example that we're going to talk about. And it's a little bit gross, but it's also really fascinating, one that you can sure to inspire some interesting dinner table conversation. We're going to talk about earwax. Okay, now earwax comes in two types, soft or hard. Okay, now you probably never thought about it before, but you have either soft earwax or hard earwax. Okay, so soft earwax are kind of, if you stick your finger in the ear because it's a little bit itchy and it comes out all gooey. Hard earwax is the sort of stuff that never comes out and tends to just form a kind of a hard kind of clump that might block your ear in the end. Okay, but so earwax tends to come in soft or hard. And so you have two versions of the earwax gene. Okay, so just as we mentioned before, one from mum and one from dad. Okay, so we're gonna say that the soft version of this gene is a capital W, okay, for wax, and that hard is going to be a lowercase w. Okay, so soft is going to be so soft comes about because of this version, and then the hard kind of comes around because of that version. All right, so let's say, so remember, so we've got two copies of each gene, two versions or two alleles of each gene. Okay, so let's say your mum has soft earwax and has two versions of the soft earwax gene. So this is mum, okay, and your dad has hard earwax. He has two versions of the hard earwax gene. Okay, and your parents come together to make you. Okay, and let's say that you've got some siblings. You're one of 4 children. Okay, now what we know is that you're going to, that there are going to be one of each of these genes that come down into every one of their children. Okay, so mum is always going to pass on a capital W to everybody. And dad's always going to pass on a lowercase w to everybody. Okay, now there are a couple of things that could happen here. You could have medium earwax, like thinking through some of the possibilities here, medium earwax, or it could be you know, maybe it's kind of, in some kids it's soft and some kids it's hard. Okay, but what we have in each of these situations is that every one of these children would have soft earwax. Okay, and so then, so that we see that even though you've still got one of the hard earwax genes, you've still got a lowercase w for everybody, that not everybody, nobody actually in this case, will have hard earwax, unlike Dad, who does. And it has to do with the fact that that in this case, that hard earwax, we only get hard earwax with both copies of the hard earwax gene. Okay, so it's only when we've got two little w's that we get hard earwax. But if we've only got one of our big W, so we could have two or we could have one, means that we have soft. So we will have soft earwax even if only one copy is present. Okay, so you could have two or you could have one. Either way, you will end up with soft earwax. I told you this was a lovely conversation, but it helps to illustrate an important point, is that these two genes are not equal. That what we would say is that the soft earwax tends to dominate the other. Okay, that you will get more often, you will have soft earwax than you will have hard earwax. And so what we use is, we use a word over here. I'm going to write it over here. We say that the soft earwax gene is dominant. It dominates the you know, it takes over. And whereas the hard earwax gene is recessive. Okay, and so that we see that it tends to be masked, or that even if, you know, if it's present there, you don't have any hardness in that earwax, that it's kind of hidden by the soft earwax gene. And so then it kind of then you start to see that it gets a bit interesting when you, with your soft earwax and having a big and little w, have children with someone else. So let's say in this situation that you've got your mixture that's soft, and then you happen to marry and have children with someone else who has the same combinations of genes that you do. Now, obviously, you don't know this when you marry them, you know, but let's just say that this is what happens. Okay, so then what's going to happen in terms of the probability is that you've got a 50-50 chance of picking either gene from you and from your partner. And so we'll probably get someone who's got two capital W's, someone who's got a capital and a lowercase w, someone who's got a lowercase and then a capital W. No, I'm still going to write it like that. You'll see why in a bit. And then one poor lucky sod who's going to get both lowercase w's. So what you get is that 3 out of the 4 children that you and your partner have will have soft earwax, and only one poor sap will have the hard and difficult earwax to deal with. Okay? So confirming that we only get hard earwax when you have 2 copies of the same gene. Okay? If you've got even 1 copy of our soft earwax gene, then you get soft earwax. If you have the dominant gene, then that is the feature that you get. Only when you've got 2 of the recessive gene do you get that feature. So what that means then is that the hard earwax seems to have skipped a generation. That from your parents, that your dad had hard earwax, and you and your partner don't, but then one of your children does. So it seems like the gene skips over the generation because you carried this gene. Okay, so we would say that you guys are carriers of the hard earwax gene. You had it, had it, but it didn't show up. But not, we would say, not expressed. Okay, so we use that kind of terminology in terms of that it didn't give rise to the feature that gene would make. Okay, so thinking in this lovely conversation about Earwax, so that we're seeing that genes can come in two different types, depending on, this is just in terms of how likely it is that we see that feature, not that there's something necessarily about the code that means that it's stronger than the other code or anything like that. It's just, we're just seeing, all right, well, if you have the gene, how does it play out in your features? And so we're seeing that some genes are dominant, that will be expressed if there's only one copy, or they might be recessive, where they will only be expressed. You will only get that feature if you have two copies of that same one. So it's less common. Okay, but it's definitely, those genes are there, and then they get passed on. They have the chance of being passed on from parent to child. Now, you can see, or one of the implications that we have here is that then when you get diseases that are genetic, so things that happen where it's a defect in the genes that then gets passed on from generation to generation, that then it's a little bit like rolling the dice when you have children as to whether you pass on the faulty gene or you pass on the healthy gene. And so with things like hemochromatosis, which is one really common genetic condition to do with the storage of iron, or we get things like the other examples are like the BRCA1 or BRCA2 genes, which affect can affect the incidence of ovarian and breast cancer in lots of people. So Angelina Jolie was one particular example that identified that she had this faulty gene, which leads to a significantly higher risk of developing breast or ovarian cancer in your lifetime, and so then often needs, and is very common in families to very high rates of getting those cancers. Okay, so seeing that when you have genes like that, then being able to predict how it gets passed on and how it affects the family tree has much more serious implications than it does whether you got soft or hard earwax. Okay, so I realize that this is quite a lot of complicated ideas here, and trying to do it. In the next kind of video, we'll look at, all right, well, once we start with particular kind of genes, how can we make some simple predictions about what the chance is of different combinations? So yeah, stay tuned for that. All right, thanks very much for watching. Bye for now.